Find a polynomial with integer coefficients that satisfies the given conditions. Q has degree 3 and 0's -6 and 1 plus I. Okay, so when we talk about polynomials of certain degree, what that means, the degree is going to tell me how many possible zeros that I have. And since Q here is a degree 3 polynomial, there are going to be 3 roots. That doesn't mean that they are necessarily going to be distinct. For example, if I simply have the polynomial x cubed equals 0, that means that x equals 0. It's a degree 3 polynomial, but it has roots of 0. And it has multiplicity 3 for those roots. Now, in this particular instance, for this example, we're already told that we're given a 0 of -6 and a 0 of 1 plus I. The -6 is a real root. The 1 plus I is a complex root. One of the things to remember about complex roots is that they always occur in conjugate pairs. So if you have a root a plus bi, which is going to be a general form of a complex root, you're also going to have a root a minus bi. So therefore, I know automatically that while this is a root 1 plus I, since it's a complex root, I will also have a 1 minus I. So now I have my 3 zeros, and they are distinct, which means that I need to go ahead and determine the best way to figure out what my actual polynomial is. Now remember, over here on the right-hand side, what I did is I took the cube root of both sides of this, and I ended up with x equals 0. Now, let's just examine this for a moment. Let's say, example, that one of the roots of some given polynomial, it doesn't matter which one, it's not this one that we're going to be working on in a moment, but let's say that one of the roots was -4. That means that I can write that as x equals -4. And in fact, if I add 4 to both sides, I now have x plus 4 is equal to 0. And the reason that I want to do that is because this becomes a factor of the given polynomial. Now that was an example of just one root. So let's go ahead and let's look at Q has degree 3 and 0's -6, 1 plus I, and 1 minus I. And I'm going to use what we just talked about as an example. So we'll start with this. X is equal to -6. That's a root, which means that I can rewrite this as x plus 6 equals 0. That x plus 6 becomes a factor of my given polynomial. That's my first factor. Now what I'm going to do is look at the other 2 roots. We'll start by stating simply that x is equal to 1 plus I. I'm going to use the same technique, and I'm going to subtract the entire expression 1 plus I from both sides of the equation. Really, what I'm doing is subtracting 1 and subtracting I. So let's examine that from that point of view, because I'm distributing this negative over both of these. So if I do that and subtract -1 here and subtract I here, I have to do that on the left, which means I have x minus 1 minus I equals 0. Now what I've done is I've come up with my second factor. Now we're going to look at the third factor. And we're going to do a couple of different things here. So, we're going to take the x equals the third factor of 1 minus I, which means that I am going to subtract 1 from both sides and add I to both sides. And I end up with x minus 1 plus I is equal to 0. That's my third factor. So at this point, now that I have three factors, what I can basically state is that q of x, which is my polynomial, is going to be equal to the first factor, x plus 6, times the second factor, x minus 1 minus I, times the third factor, x minus 1 plus I. Now, obviously, we need to go ahead and multiply this out. It doesn't really matter how you approach this, because at some point you've got a trinomial times a trinomial, which is not fun to actually multiply out. Fortunately for us in this case, this is a simple polynomial, comparatively speaking. So what we'll do is we're going to multiply the two trinomials first. So if I take x minus 1 minus I, and I multiply that by x minus 1 plus I, I'm going to use a distributive property. X here will multiply the three terms in that trinomial. So I'll have x times x, which is x squared, x times negative 1, which is negative x, and x times positive I, which is plus xi. Then we'll take the negative 1, and we'll multiply that by the three terms in this trinomial. Negative 1 times x gives me a negative x. So negative 1 times negative 1 will give me a positive 1. And what I'm going to do is I'm going to write that over to the right somewhere, because eventually I'm going to try to line up like terms. Then I'll have negative 1 times I. So we'll write that as a negative I. Now, we're going to do this again with the third term in that first trinomial. We're going to multiply negative I times x, negative I times negative 1, and negative I times I. So negative I times x is negative xi. Notice that I've lined it up with the positive xi in my first expansion. Then we're going to have negative I times negative 1. That's going to give me a positive I. Notice that once again, I'm lining it up with a like term. And then finally, we have negative I times I, which is going to be a negative I squared. And now what we're going to do is we're going to go ahead and we're going to add our columns, our like terms. This x squared is simply going to be x squared. There's nothing I can add or subtract to it. In this column, we'll end up with minus 2x. In this column, that's going to go to 0, so I don't have to worry about it. Then we'll have this plus 1. Once again, in this column, that's going to go to 0, so I don't have to worry about it. And then I have this minus I squared. But remember that minus I squared is going to be a negative 1. Because remember, I is equal to the square root of negative 1. Therefore, I squared is equal to negative 1. And notice that I wrote it in parentheses. And so, instead of having negative I squared, I'm going to have negative 1, which is going to be a plus 1. And so my polynomial is x squared minus 2x plus 2. Now, that I'm going to take and I'm going to multiply it by x plus 6. So q of x is now the quantity x plus 6 times x squared minus 2x plus 2. And I'm going to use the distributive property here also. We'll go ahead and say x times x squared, x times negative 2x, and x times 2. That gives me x cubed minus 2x squared plus 2x. Then we take the 6 and multiply it by x squared, by negative 2x, and by 2. So 6 times x squared is 6x squared. 6 times negative 2x is negative 12x. And 6 times 2 is a positive 12. And we're going to do the same thing that we did just above when we multiplied the two complex components together. This simply becomes x cubed. Negative 2x squared plus 6x squared, because I should have put a plus sign there, is going to be 4x squared. And 2x minus 12x is a negative 10x. And in this doesn't change. And so now I have my polynomial q of x is equal to x cubed plus 4x squared minus 10x plus 12.